Okay, welcome back, everybody. As I mentioned, today should be fairly light. Last time we talked about some stuff that was not super light, sort of complex material. But it was all about the thermohaline circulation, also called the Atlantic Meridional Overturning Circulation, that goes by the acronym the AMOC. And the AMOC is this conveyor belt type circulation that sort of flows north at the surface level in the Atlantic Ocean, sinks in the high latitudes, then we have sort of upwelling throughout the domain, throughout the basin, and then we have acute upwelling happening in the Southern Ocean. And then we also have these two branches with Antarctic bottom water and North Atlantic deep water. And so the first diagram here shows a slice of what the Atlantic looks like in terms of its water masses. This one's a bit reversed in a weird way. So Greenland, the northern hemisphere, is up on this side, the equator's in the middle, and then Antarctica, the southern hemisphere, is down on the right-hand side. And it's showing how sort of the thermohaline circulation gets started. So we talked about these two different kinds of currents. There were surface currents, and then there were the deep currents. And the surface currents are generally driven by wind, because we have just mechanical forces acting on the surface of the ocean. But that can only drive surface currents, because that's the only part of the ocean that the wind actually makes contact with, is the surface. But then there are also deep currents, and those deep currents are mostly driven by density differences. And when we talked about the equation of state and the properties of water, we said there are two main factors that affect the density of seawater, and those are the salinity and the temperature. So that's why we call it the thermohaline circulation, because it's driven by density differences, which are in turn driven by differences in salinity and density. So one big controlling factor for this thermohaline circulation is deep water formation. And what we mean by that is in the polar regions, so in the North Atlantic, and so this is the Labrador Sea and the Irminger Sea, Nordic Seas, the surface waters get very cold there, and they're also fairly salty. And they get so cold that they get denser than the surrounding waters, and they sink down and form deep waters. And the same thing happens down by Antarctica. We have very cold conditions down near the Antarctic continent. We have also sea ice forming. We're going to talk about sea ice today. That also tends to make the water very salty. If you sort of go back and look at your notes, what happens is the sea ice freezes at the surface, but the salt doesn't like to get into the structure of the ice. Salt ions don't fit well into the molecular structure of ice. So the salt gets ejected at the bottom. So we have very cold water here, and also it's salty from what's called brine, that process called brine rejection. And so you sink all the way to the bottom, and then that Antarctic bottom water, as the sort of name suggests, it fills up the bottom part of the abyss, so that the lowest levels of the Atlantic Ocean are filled up with this water that came from the surface near Antarctica. And the North Atlantic deep water, very similar mechanism. We get very cold atmosphere. Also, there's sea ice stuff going on here, and the water sinks. It just turns out that because of the northern polar and the southern polar are not exactly alike, the Antarctic water is a little bit colder, so it gets all the way to the bottom, whereas the North Atlantic deep water kind of gets into the middle, and it sits in a layer on top of the Antarctic bottom water. And so there's sort of two directions of deep water formation happening. Both of them sink down and spread out, but one of them happens from the south and then spreads north, and the North Atlantic deep water sinks down in the north and then spreads south. We talked about how these things set up a circulation and transports heat and so forth. But then a really interesting sort of and scary aspect of the circulation is that when we measure the circulation, so these two plots in the middle here are time series, where the x-axis is time going from 2015 up to about 2019, and the black line here is showing the strength of this sort of circulation that we have here, the strength of that circulation year over year. We measure this with this observing, very expensive multinational observing array called OSNAP. And what you see in this diagram is that it's very sort of noisy. It bounces around quite a lot. And if you look over some particular periods, it could double or more than double over the course of less than a year. And so that amount of variability, it's sort of the opposite of steadiness and stability. It's sort of changing all the time in these pretty dramatic ways. And that makes one wonder, could there be even larger changes? Could this system be in some sense unstable? And that's where we got into this diagram at the bottom right. So in climate, there's a challenge in understanding climate fundamentally, which is that, you know, if you're trying to understand, say, crystal structure of rocks or something, let's say you're doing geology, mineral crystal structure, you can get many samples from the field of different examples of that mineral, and then run them through X-ray diffraction machines and do all sorts of things, and you can get lots of data on all these different samples, show either similar things or they show different things. And then you could even change them. You could heat the rocks up or cool them down or put them under pressure and make all these measurements. So you have the ability to do controlled experiments, right? You can play with the system many different ways, collect lots of data, and try to understand based on that approach how the system is going to behave or what its properties are. With climate, we don't have that luxury because we have one Earth and we only have one climate system. And we can't really experiment with it in the same way that we can with smaller scale systems. And what we kind of have to rely on is looking at natural variability, like things like sunspots or Milankovitch, paleoclimate. And then also the fact that we're sort of conducting sort of one big experiment with global warming. So we're putting more and more carbon in the atmosphere, and that's causing the climate to change. And by understanding the response that we can measure, we can understand something about the climate system. But so fundamentally, because of that limitation that we only have the one Earth, and we can't do climate scale experiments very easily, a lot of the work on understanding the climate system is based on models. And so we try to make sort of more and more realistic models, global climate models and things like that, to investigate the potential for different pieces of physics to happen. And so this figure is an example of that kind of analysis that comes from quite a while ago in the 1990s, where they took an ocean climate model. So it didn't simulate the whole atmosphere, it just simulated the ocean, and they played around with a sort of a model of melting Greenland. So one of the big worries with the AMOC circulation is, as we warm the climate by emitting CO2, that encourages melting of glacial ice, and then when that glacial ice melts, that fresh water goes into the ocean ultimately. And so when you add fresh water here, so in the North Atlantic, when you start to melt the Greenland glaciers, they put fresh water here, and when you freshen the water, you're going to make it less dense, and so it's going to be less likely to sink. And so the question is, would that affect this deep water formation, and would it affect this sort of global circulation that's happening? This guy Ramsdorff did an experiment with the computer model where he did that. He sort of simulated melting Greenland. And then what he found was that as you melt Greenland more and more, the circulation weakens, and that makes sense because you're making it harder for that surface water to sink, so the circulation weakens as you add more and more fresh water. But then the amazing thing that I think no one really anticipated is that there were certain points that we call tipping points in the system, where you might have seen this in sort of popular discussions of climate change. And in the model, there are these tipping points where as you increase the meltwater from just right here to just a little bit to the right, there's this vertical drop in the strength of the circulation. So rather than getting a gradual decline, you get an abrupt collapse. And then there were actually several of these abrupt collapses that happened at different points in the model. And you can think of those abrupt collapses as places where the circulation sort of reorganizes in a big way. And then the other thing that they found was irreversibility. So when they took the melting water, the meltwater away, and then they went backwards on this diagram, they didn't recover the previous climate. The AMOC remained shut down until you actually started putting in salty water, essentially, to kickstart it, and then sort of you get back to the previous climate. So there's this potential for tipping points involving the AMOC, which could lead to sort of dramatic global climate change. And then there's irreversibility in the system, so that if you cross those thresholds, it may not be so simple to go backward. Okay, so that was sort of the end. So this AMOC discussion was sort of the end of our look into the deep currents. So we talked about the surface currents, we talked about the different main circulation features going on in each basin. And then the AMOC was sort of the end of that. And so now today we're moving on to a short topic on the cryosphere. So sea ice and then glacial ice and marine terminating glaciers we're going to talk about. And then after that, maybe the last bit of the class, we're going to get into waves. And so Waves and tides are the last big section of the course. We're going to talk about sea surface waves, so that we're all very familiar with, but that's a very deep area where there's a lot to understand about surface waves. And we'll also, I think, hopefully get a chance to look at some of the most modern observational systems. There are some really big advances in ocean observational systems that are useful for waves that have just sort of been put in orbit over the past 5 years or so. So these, and then tides at the end. So we're not going to talk about tides today, but in a few classes we'll start to talk about tides, and tides is also very interesting and very, very relevant if you do anything with marine biology or coastal or ports or anything like that. No, understanding the tides is very, very central. Since that's kind of we often don't think about them that much because on the global ocean, it's funny. If you look in the middle of the ocean, the tides hardly do anything. The sea surface might go up and down by an unnoticeable amount. But then you go to the Bay of Fundy. We all probably are familiar with that location. But the tides can be 20 meters or something. There's places where the tides are enormous. Maybe it's 20 feet. I'm not sure. But the tides in Bay of Fundy are huge. So let's get started. So the first topic today is on sea ice and glacial ice. And so in the book, if you're using the book, this is back covered in chapter 6. So we've kind of gone past chapter 6, and this is just a rewind. But so I just want to ask a question at the beginning and see sort of where we're sort of at. So can anyone tell me what's the difference between, first of all, let's just focus on these first two. What's the difference between sea ice and icebergs? What's the difference? Yeah.
Sea ice is water in the ocean that's frozen.
Correct.
Icebergs are chunks of glaciers that are cracked up.
That's right. So sea ice is frozen seawater. Right? This is exactly what you said. So the surface water, say in the North Atlantic, this atmosphere gets very cold, that cools down the surface layer, and then that water just freezes. Even though it's salty water, so it's harder to freeze it than it is to freeze fresh water, but it freezes anyways. You have sea ice at the surface, and then icebergs are cracked off of glaciers. So icebergs, ultimately the source of the water is from precipitation, because the rain or the snow falls on the glaciers, freezes as ice, and then breaks off as a chunk and floats away. That's an iceberg. What about ice shelves? Can anyone tell me what an ice shelf is? That's a bit more specific, and that's not as much common knowledge as the other two. But an ice shelf, and we'll talk about this, is sort of the edge of a glacier. So when you have a glacier, often the glacier sort of ends in the water, and there's a part of the glacier that's kind of partially floating, and that's called an ice shelf. So we're going to come back to that. Okay, so sea ice is frozen seawater. We know that. But it's more complex than just saying it freezes like a bunch of ice cubes or something. There's a specific pattern in which you form the sea ice, and there are various stages. And so we're just going to talk about, let's show some pictures and look at what these different stages look like. So when you have this cold atmosphere, if you start out with the ocean surface is liquid state, the first stage of sea ice that you get is called pancake ice, and this is this really cool looking, very delicate set of very, very small pieces of ice, maybe a meter, a couple meters across. And because they all sort of run into each other and grind off of each other, they end up in these disc pancake like shapes. And these things actually evolve from these little ice crystals that are the first thing to form. So right at the surface layer, you get these things that are called slush, so needle-like crystals that are slush, and then those things freeze together, and you call this pancake ice. So this is the first stage, and you can imagine as it becomes increasingly cold, these things that are running in together and have water lapping over them and stuff like that can actually freeze together into larger structures. And so when the pancake ice, it freezes together, you get these things that are called ice flows. And so what exactly is an ice flow? Many things in the discussion of sea ice, they're a little bit vague at the edges. What's an ice flow versus what's a large pancake? You sort of need to draw the line somewhere. But generally, when we talk about ice flows, we're saying that they're more than 20 meters across. So an individual pancake might be 1 to 2 meters. You freeze 10 or 20 of those things together, and you get these regions of frozen sea surface. And these large pieces of ice that can be 10, 20 meters across, and that's when we call those things ice flows. And they can have different shapes and sizes. Here's a very cool picture of the ice flows into Hudson Strait. So it's, I guess, taken from a helicopter. And so Hudson Strait is right here. So there's Hudson Bay and Hudson Strait. And so you see this aerial photo, these very, very large pieces of ice. And you can imagine these things drift around, they maybe break apart. They're subject to the action of waves. So as waves go through, they bend these things and maybe cause them to break apart, or they can cause different ice flows to merge together. And There's actually a lot of sort of modeling, actually sort of like heavy-duty theoretical physics work involved in understanding what determines how big these things are and the distribution of how ice flows take on different sizes. Here's another cool picture. So this is down in the Southern Ocean. So a very important part of the Southern Ocean near Antarctica is the Weddell Sea. So there's this region here. So this is the so here we have this little inlet here called the Weddell Sea, and then this region here, sort of the closest, the narrowest point of the Southern Ocean. This is called the Drake Passage. And we have this sort of peninsula here. This is West Antarctica. The larger part is called East Antarctica. But in the Weddell Sea, this is obviously a historical photo. You also see these large ice flows. So it happens in the northern polar environment, and then also in the South Pole. So these ice flows move around under wind action, the action of the surface currents, and then the waves as well. And then these flows, if you imagine, so the minimum size for a flow is around 20 meters, but they can be much larger than that. And so this ice is quite heavy. So as these things move, they're drifting. They have quite a bit of momentum. And so when they hit each other, there's a lot of force involved. And so when these large ice flows collide with each other, the ice sort of piles up at the interface. They may freeze together, and at the place where they collided, you get this ridge of all this sort of broken pieces of ice all piled up. And so here's a person for scale. So this is sort of much larger than a person. And those things are called pressure ridges. And so these are very common to see at the locations where large ice flows merge with one another. And that's just due to the very high amounts of mass that are involved in these ice flows. Okay, so a little bit about the physics of how sea ice forms and the rate at which it forms. And so all these things, actually, I'll just mention, are very important to understand for, say, climate change predictions, because if we want to understand how the climate's going to change in the future, or understand the current climate change we're going through, albedo has a big effect, so how much solar radiation we're reflecting back out to space. And so the more ice you have, the higher the albedo. And predicting how these things change from year to year requires some kind of model or understanding of how the ice actually grows. So let me see, do I have a... I don't. So I don't have a marker. So okay, so we'll explain this just verbally. So obviously, so the rate of ice growth depends on the temperature. The colder it is, the easier it is to grow ice. That makes a lot of sense. But as the thickness of the ice increases, actually the rate of growth gets slower. So as the ice grows and you get a thicker and thicker layer, it actually starts to grow more slowly. So you get a thicker layer of ice, and now it slows down. So it might grow initially quite rapidly, and then it slows down as it gets thick. And the reason for that is the sea ice freezes from the bottom, so it's frozen seawater. So you're not adding ice to the top, unless maybe you have precipitation, but you're adding ice to the bottom as you freeze that layer of seawater that's right underneath the ice. And that freezes because of the cold temperatures. But the atmosphere is quite a bit colder in these polar regions than is the ocean. So really it's the contact with the cold atmosphere that causes the ice to freeze. And so if you imagine, if you have a thick layer of ice, let's say it's a meter thick, right? So now the base of that layer of ice is now 1 meter separated from the cold atmosphere, and there's actually an insulating layer of ice above it. And so the basal layer, which is where you're going to get freeze-on happening, is protected. It's insulated from the cold atmosphere. And so as the ice gets thicker and thicker, it grows more and more slowly, and you have to have an even colder temperatures to grow that ice. Similarly, I guess, if you had a very warm summer and you're melting ice, as that ice gets thinner, now the base of the ice is brought up closer to that warm temperatures, and so you're going to have faster melting. So this is something else that I mentioned, brine rejection. So brine is just a qualitative word we use for very, very salty seawater. So normal salinity is 35 parts per thousand. If you're way above that, I actually don't know the official designation for how salty it has to be called brine, but this is extremely salty water. You can see it by eyes. If you actually were watching ice forming in a glass of salty water, you actually see this cloudy stuff coming out of the bottom. It's very, very salty. And then because of index of refraction differences and stuff, you can see this stuff coming at the bottom. And so the salt that's in the seawater doesn't like to be in the crystal structure of the ice, and so it just falls out the bottom in liquid form. And that means that you have very, very salty water that's right underneath the ice. And that water is also very cold, so that'll tend to sink down. And so you sort of have this brine that's rejected from the bottom of the sea ice that's going to sink down, and that's replaced by cold fresh water from the surrounding areas. So key ideas here is that obviously when we have low temperatures, cold atmosphere, that promotes ice growth. But then as the ice gets thicker, it starts to grow more slowly because of the insulation effect. And then the third thing is we reject this very salty water out of the ice structure, and that's called brine. Okay, so that's sea ice. So a couple of very simple statements here on icebergs. So icebergs break off of glaciers. So they don't form from seawater. They crack off the side of glaciers, and we're actually going to talk in a little bit of detail exactly how that cracking off process happens. And they look like this. So they look quite different. They're often much taller than what you get from sea ice. You can see there's sort of some cleaving structure here, like you know how when you bite into an apple, right? There's like planar structures because it cracks off, right? And the ice is kind of like this. It's not all jagged on the side. It's like it cracked off as a coherent piece, and then it'll melt after that. And so totally different from sea ice. And this is basically the ultimate source of the water for this icebergs, this precipitation that fell, say, over Greenland or on the Antarctic continent. Okay, so exactly how does this process, when we say it breaks off of glaciers, there's a technical term for that, and it's called calving, like calving. And calving just means breaking ice off. It's just a special word when it's ice, it's the thing that's cracking off. And so then we're going to sort of dive into a little bit, how does this calving or cracking off process actually happen? So this is a diagram of what's called a marine terminating glacier. So marine terminating means, the rest of the land is over on this side. So here's the base of the glacier, so this is the land. And then the ice is sitting on the land, so it's called grounded ice. So the land is frozen so the ice is frozen onto the bedrock underneath, or maybe there could be soil or subglacial dirt and things like that that are on the bottom. And then the ice extent goes to a certain point, and then the continent might be sort of sinking down. You might have going on towards the continental shelf. The ice ends at a certain point, and the end of the glacier actually makes contact with the ocean. So that's what we mean by marine terminating. So the terminus of the glacier is where the glacier ends. So it extends far back inland this direction, and it ends here, that's the terminus. And the terminus runs up against the ocean. So it's a marine terminating glacier. As you can see from this diagram, and I'll just tell you explicitly, so often on tests and stuff I get you to label a diagram. This diagram is much too complex and far afield, so you won't have to label this one. This is a bit too complicated. But understanding the basic features is worth it. I happen to know a little bit about this because when I was doing my graduate school, I shared an office with a guy who worked on this exact thing, marine terminating glaciers in Greenland and Antarctica. So I would he would tell me about his model wouldn't work and things like that, and he would tell me about all these problems. So as you can see from this, the glacier is pretty complicated. There's a lot of stuff going on. So let's point out a few interesting features of these marine terminating glaciers. So one thing is it's full of holes. So there's all these cracks in the top. These things are called crevasses. And actually, if you want to do, these systems are so complex that one important way that we have to understand to work on them is actually go to the glaciers and make observations. It's very hard to make just mathematical theories and stuff without actually going to these glaciers and looking at them. But these crevasses make the glacial work extremely dangerous because these things can be really deep. As you can see here, these things can be maybe half the way down, so the glacier is thousands of meters thick maybe, and these, you can, and what they often try to do is land a helicopter or drop people onto the surface of these glaciers. There's snow blindness issues. There can be snow covering the tops of these things, and people have unfortunately died falling into these holes trying to study glaciers. But they also have so it's very scary. It's very scary work. Only the bravest people work on these glaciers. They're known to be very, very dangerous. But these crevasses, they actually are critical to the way the glacier actually functions. Because you can see on the bottom, so here's a cutout. So the glacier, this square hole's not really there. That's just to sort of help you see on the inside. But you can see underneath, there are these little rivers on the bottom. And these are called subglacial channels. And the whole network of these subglacial channels is called the subglacial hydrology. And what happens is, during the summer period especially, we have sunlight coming down onto the top of this thing, and it's creating meltwater. And you can actually get large pools of meltwater that are visible from satellites, like lakes, that are basically forming on the surface of these glaciers. And what can happen is, when you form this meltwater on the top, the meltwater gets into these crevasses, and then the pressure of the water helps to open them up and melt them more. And at some point, these crevasses can actually develop cracks that lead all the way to the bottom of the glacier. So you get the sun coming down, meltwater on top, the cracks get deeper and get opened up by the pressure, and then the water actually drains to the base of the glacier. So there actually are some spectacular observations. I'm afraid I don't have them here, actually. I should put it in. But where there's a big, basically glacial lake, so a huge pool of meltwater sitting on top of the glacier, and then all of a sudden some hole opens up at the bottom of that, and the whole glacier lake just drains out over the course of like maybe a day, right into the base of the glacier. And so you can imagine, when you pour all that meltwater down into the bottom, it's going to affect the soil, and you can actually have a layer of water at the base of the glacier that the glacier kind of floats on and slides on and slips over. So when you drain all this water from the surface meltwater down into the subglacial hydrology, you can affect the sliding of the glacier. It can actually start to move a lot faster. So when you have these events where like glacial lakes drain into the base, you can actually see differences in the sliding rate of the glaciers. Because I should mention, these glaciers actually move. So that's a fundamental point. So the glacier over time, if you took a bucket of red paint, you made a dot here on the glacier, and you looked at it from space over many years, that dot would migrate from the back to the front, and eventually you would see it crack off in an iceberg and float away. And these the rates of speed are very slow, but we can actually track these, and it has been done to track using satellite imagery, points on this glacier actually flowing downstream. So over long time scales, the glacier actually kind of flows like a liquid very slowly. And then that rate of flow is connected to what's happening at the base. Okay, so that's sort of the sliding of the crevasses. So what's happening right at the terminus? So right at the terminus, we have these crevasses that are near the edge, and those can actually cause pieces of the glacier to break off. And it creates this bunch of floating stuff. Like basically, there's always like a bunch of floating icebergs and sort of glacial debris that are called the mélange, at the bottom here, M-E-L-A-N-G-E. And what that does is it actually kind of holds back the tip of the glacier, because as the glacier wants to flow forward out into the ocean, it has to press up against all of these buoyant pieces of ice that it has actually have cracked off of it, and they kind of push back a little bit. And prevent the glacier from flowing out into the ocean. Okay, so this is kind of the basic setup. We've got our glacier, it abuts the ocean, we've got subglacial channels, we've got meltwater on the surface, and we've got all these crevasses. Okay, so this tells us, this is sort of the basic setup for the story on how we generate icebergs. Obviously, cracking a piece of a solid off another complex solid is going to be a complex thing that can happen many different ways. You know, icebergs have different shapes and sizes, but there's a few different mechanisms that are sort of typical mechanisms for how we generate glaciers, and they're both tied to these crevasses. So here's one example at the top. So imagine we have at the edge of the glacier, here's our terminus, and we have a crevasse that's near the edge. At the top of the ocean, we have to tend to have the warmest water. So generally, you have the surface is warmer than the deep, because otherwise the cold water at the surface would sink and they would exchange positions. So you tend to have the warmest seawater at the surface ocean, and so that can start to melt out and sort of undercut this block of ice at the top, this erosional notch as they call it. And as that builds up, or as that thing grows, and our crevasse propagates down from the surface, maybe there's meltwater happening, this whole thing can crack off, and so we get a piece from sort of the upper half of the glacier, calving off and then floating away as an iceberg. And something very similar can happen from the bottom. So if we have a crevasse, or so I don't know if it's actually called a crevasse, but we can have a crack from the base of the glacier going up. And then as this thing is sort of partially floating, it experiences buoyant forces. So essentially, if it wasn't connected to this glacier, it would want to pop up to the surface and sort of float away. But because it's connected, it's being held on, and there's kind of torque happening at this point where the buoyant forces want to rip this off this way, and then the molecular cohesion forces happening inside the crystal structure of the ice are holding it on at the top. And so if these buoyant forces get strong enough, maybe if we sort of have maybe this crevasse deepens or whatever, you can crack this piece off and it can float away also. So you can have calving from the top, or you can have calving from the bottom, but both of them can produce large pieces of ice that float away. So what happens to these icebergs once they calve off the glacier? Well, we know we see them here in Newfoundland. So here's a schematic picture. I think this is from the book, where these triangles are many places where we've seen iceberg observations here near Newfoundland. The X is the Titanic, connected to icebergs in history. But what happens is most of the icebergs that we see here in Newfoundland calve off of Greenland. So Greenland has all these glaciers on it, and most of the icebergs that we see actually calve off Western Greenland. So this is the western side, and the icebergs. There are these fjords and things where we have glaciers that are going out into the sea, or the ocean rather, and then those calve off. And then the icebergs get caught up in the Labrador Current mostly, and so that's why the Labrador Current is strongest along the coast here. And so we have this band of icebergs that sort of hugs the coastline and then delivers the icebergs down to near Newfoundland. But very interestingly, also icebergs that calve off the eastern side of the Greenland glaciers also can come around, wrap around the tip of Greenland. This is called the East Greenland Current. Come up around the other side and then get embedded into the Labrador Current and come down that way. And so because of sort of this whole network of currents that we talked about in the North Atlantic, we can get glaciers actually from either side. And you can imagine there'll be different ages, right? The ones that come from the eastern side of Greenland maybe take longer to get here than the ones that come from the western side. And of course, these have all sorts of implications for, travel on the ocean. In offshore oil industry, these things are of major importance. Actually, I'm not sure if people know this, but something that's done regularly is if there are icebergs that are approaching offshore oil operations, like say Hibernia platform or whatever, they will actually send out boats to attach cables to the icebergs and actually tow them physically out of the path so that they don't run into basically the poles that hold up the drilling operation. And so there's all kinds of observational systems and practical systems for dealing with these icebergs, and very important for navigation and for offshore operations. Okay, so what is an ice shelf? So we actually sort of already saw ice shelves a little bit in the marine terminating glacier. Oh, sorry, this is a little bit hard to see. Maybe if I turn down the light a little bit. Just for now, I'll turn this down. So what an ice shelf is imagine you have a marine terminating glacier. So the glacier goes back this way, all sorts of thick ice back here and land. And so now it ends, and there's a point at the base of the glacier called the grounding line. And that's the furthest point into the water where the ice is making contact. It's kind of frozen on to the base here, the bedrock or whatever kind of sea floor you might have. And then the ice thins out in this tongue that sticks out into the water called an ice shelf. And these things can protrude out quite a distance, and then they calve off icebergs at the end. And so this is an example over on this side where we have a large glacier over here, and then we have a partially floating ice shelf protruding out into the ocean. So it's partially floating because it's being supported. Its weight that's if you drew a free body diagram, right? If you took the ice shelf, there'd be a force pointing down. That's the gravitational force. That's partially but not completely balanced by a buoyant force. But then there's also contact forces, or there's is basically being held on this side by the larger part of the glacier. So it's partially floating, but not entirely floating. And you can imagine, these things look kind of intrinsically unstable a little bit, because like, could this whole thing just crack off and float away? And so the answer to that is yes, and this happens sometimes. So this is a very spectacular example from a few years ago now, 2017. So this is the Larsen ice shelf. So this is down in Antarctica. And this aerial photo, it's hard to see, but this piece of ice is the size of the state of Delaware. Now most people, I don't know how big that is, but it's half the size of the Avalon Peninsula. So you drive across, you drive to the other side of the Avalon, half that distance, it's one huge sheet of ice that just cracked off Antarctica and floated away. So this is the kind of thing that, like, if this thing melts, you might imagine that actually has a noticeable effect on the planetary albedo. That's a ton of ice. And this just floats away and melts. And so these ice shelves are sort of notorious for their potential for instability, but they're all over the place. Antarctica and Greenland, and any place where you have large marine terminating glaciers, this structure just develops spontaneously, and then you can imagine if you have crevasses and stuff happening at the end of the ice shelf, this whole structure could just float away sort of coherent. Okay, the next topic is getting on to waves, but I think since we only have a few minutes left anyway, I think I'm just going to stop it there. And we'll pick up on Wednesday with surface waves, where we're going to talk about how waves are categorized, different types of waves like transverse waves and longitudinal waves and that kind of thing, and then tie it into how waves at the sea surface work and how they're connected to wind and storms and things like that. But I'll break there, and I'll see everybody on Wednesday. Oh, and you had a question. Okay, you just come up after, and we can talk about that. Okay, great. Bye.